parameter to look at the data, estimate parameters, and we would like to do it when the data set, the samples of the data is pretty as small as possible. We would like to have accurate estimation, of course, and as we said, we would like they to be unbiased, not to overshoot, not to undershoot. So how could we do parameter estimations? Let's mention the law of the large numbers. It would be from our previous lecture that essentially says that if we look at any sample set and the sample goes larger and larger, and at each moment for every set that we have in mind, we look at the average of the set. And now as the set becomes larger and larger, law of large number says we will go closer and closer to the true average of the whole population. And the central limit theorems needs many more assumptions. It needs to assume that we have parameters that are variables, that are independent of each other. How much money you was born with, how much money you'll inherit through your life, and let's pretend that these two parameters are independent of each other, and furthermore, let's assume that each distribution is the same distribution, and we sum up how much money you have in total, giving these two parameters. And let's add more and more parameters. Again, independent, all comes from the same distribution, and look at what pick 10 people from the population, ask how are these numbers distributed, another 10 people. Another 10 people ask for a set of 10 people, how will they be distributed? Now let's take 11 people. How will the average be distributed? Yada, yada, yada. It will always look like a Gaussian, where the more people we have in the samples, the more we're close to the actual mean and the variance of the actual population, that it behave roughly as square root n. So just why are what's the deal with parameter estimation? Quick example. We toss the coins 100 times and we observe 73 heads, 27 tails, and we still assume that the results are independent of each other. So it's not a Markov model. You probably heard about it. The result of the ith experiments doesn't influence in any way the results of the I+1 experiment, of the next coin toss. However, now I want to ask, is a coin, given that I have such a strong preference for heads versus then tails, I want to ask, is this the case that the probability that the bias of the coin is 0.73? That is, if I'll repeat it in the 101 times, I have a 73% to get ahead. Or is it that it's actually a fair coin and we just have a lot of outliers? We landed on less likely, but definitely possible outcome, even though the coin is fair. And we would like to define formally what is the likelihood of each such event, and our guess would be, of course, the guess that all the real parameter of theta, the bias of the coin, should be the one that is the more likely that happens. If you want to go philosophy, you want to refers to Occam razor, if you wish, that essentially said if you have different explanation to the same phenomena, the simplest one is probably the most likely one, or the true one, which is might be a bit too much in the error for my taste. But you'd like to say the errors that we got are the most probable. quick example before it's becoming completely abstract. Suppose that we observe n data points, all from Gaussian models with parameters of mu, the average. Here is the average of the blue here represents the data that we sampled, but I'll assume that it's Gaussian. And I'll assume that the standard that the variance is sigma squared. That is, standard deviation is sigma. And we want to know both. So what should be our guesstimate, given that the blue is the data? What should be our probability distribution function? We can guesstimate that this is the one, but if you notice the average here is not the average of the data, so that's not very likely. So we can estimate that the average is the same average of the data, and now we need to ask what is the standard deviation, how tall and narrow or wide and shallow the curve is, and this seems to fit the data much not nearly as likely as this curve. That should be probably the right one. That should be probably our guesstimate of the phi and theta, of mu and theta, and y and sigma and y. So because the number of errors that we had is, in a sense, the smallest one. It fits the data the best. So let's introduce a new notation. We said that xi is distributed according to probability p, but here is a semicolon theta. Theta is one of the parameters that we need to have, and we'll have only two examples. One would be where each such experiment is a Bernoulli experiment. Remember, just a fancy name of tossing a coin, but n theta is just a bias of the coin. Or the case of a Gaussian, and then theta will include our both parameter, standard deviation, and mean, mu and theta, and sigma. So we would like to ask what is p that we got x1 in our first sample point, x2, x3, ... x capital N, but given that we have this set of parameters theta. And because this joint probability consists of events that we would like to assume that they are independent, what the first person that we picked has nothing to do with the second person, or the first gene has nothing to do with the second gene in the case of the toad pools and the frogs that we discussed in homework 1, in homework 2. So what is the joint probability that all these different events happen? It's just the multiplication, capital pi multiplication. If you're not familiar, it's just like capital sigma is a summation, capital pi is the multiplication, the probability that the first event happened, times the probability of the second, times the probability all the way to the nth one, but all with the same semicolon theta, the same single or multiple or vector of parameters. And what we want to ask now, the probability help us to compute for given theta, and the probability help us compute, probability theory help us to compute this number, this probability. Our question now is the opposite. We have the data. What are the most likely parameters that gives us this data? So we would like to define the likelihood function, denoted as calligraphic L. Calligraphic L, sometimes we'll add the sub index n to denote that it's set of data points, and theta are the parameters that we want to guess. For example, what is the average? What is a real average given that the sample points tell us something? So as a function of the parameter theta, the data is fixed, and we are playing the opposite game. For every possible guesstimate of theta. We have some value, give me the value that is the maximum. So that's how well the data fits the model. What is this abstract word model? Model might say each experiment is independent of the other one. Another part of the model would say each parameter is distributed, say, according to a uniform that we don't discuss today, or according to Bernoulli, flip a coin, or according to Gaussian. That's another part of the model. Another part of the model is just to say that in all these experiments, all these parameters, they have the same parameters. It's 1 mu and 1 sigma for all the parameters. That would be like a very simplistic model. We desperately need an example. Here it comes. So suppose that we are making this assumption that each one of the xi's is distributed according to independent probability function, and what is a joint probability over an independent identical distributed IID function observed for the data x1 ... xn. Desperately need an example. So suppose that x is a Bernoulli, that is like a coin, and we observed these 5 observations: head, head, tail, head, tail. 1, 1, 0, 1, 0. What is the probability for, let's assume that the coin is, the parameter theta, the bias of the coin, is 0.6. What is therefore, that is the probability of a head, in this case, would be 0.6, and the probability of a tail would be 0.4, 1 minus 0.6. How did I come up with this number? Again, that's just a guesstimate of what would be the parameter. What would be the parameters? As we'll see, that's maybe not such a bad guess. What is the probability that I got 1 in the first trial, given that these are the parameters? Well, this probability would be, therefore, just said it, 0.6 for the first one, 0.6 for the second one. What is the probability that in the first trial I got head, and in the second trial I got head, given that these are the parameter? This probability is 0.6 times 0.6, making it 0.6 squared. Now, the third trial was tail. It's for the first trial, the third trial was a tail, a 0. What its probability? 0.4 times 0.6 times 0.4. Altogether, the probability that this happens is 0.63, which makes it 0.03. It's not a high probability, but let's do the same gymnastic. But now let's assume that the parameter of a head is actually 0.2, and the parameter of a tail is 0.8. So what's the probability that I got? The very same results, the data. I don't have control of the data. What is the probability that these are the results, given that these are the parameters? Well, that would be 0.2 coming from here to, that happens 3 times, so 0.2 cubed times 0.8 squared, which is 0.01. Now, both these probabilities are quite small, but this is obviously larger than this. So this explanation, that the coin has a bias of 0.6 is more likely, has higher likelihood than that the parameter is 0.2. And once if you understood this one, then the rest of the talk is just cranking arithmetic and algebra. So, what is the idea of the maximum likelihood estimator, MLE, is it asks, if you're not familiar, yet another notation, it asks what is the maximum value of the likelihood function. In this case, the multiplication of the parameters given that we have theta. Except that what is this arg for argument ask for? It doesn't ask what is the value of the maximum likelihood. It asks what value of parameters brings this expression to the maximum value. That's what I want to guess. Going back one slide, I was not really interested in computing the probability with 0.6 versus computing the probability with 0.2. That was not the main question. It was a tool that leads me to decide which of these two probabilities is more likely, but what I really want to know is which value of theta, replace this 0.6 by theta, which value of theta brings this probability to the maximum possible given that this is the data. What did I use in all this exercise? The fact that I assume that these experiments are independent. Notice that at no point I did not ask do I care about the order. It did not influence at all my model. So for these numbers of 1 of zeros, I've got, of course, the same result. So maximum likelihood estimator, tell me what is theta that brings this expression to the maximum value given the data and giving the model. So how can I find the theta, the maximum likelihood estimator? We'll see two methods. The closed form method. Sometimes I can just compute theta directly. And in real world problems, that sounds a bit too good to be true, while iterative method is much more likely to be practical. And that's usually what the tools that we'll use, the iterative method. So how can I find in general maximum maximizer of a function? In both methods, I need to use the derivative of the function. Let's assume that I have a function like so. F of theta would be quadratic in theta minus a constant times theta squared plus b theta plus c, and I'll assume that a is positive, this first constant, so the function is monotonically going to some extreme and then going down. It would be nice if this function happens to be concave, but not really. If you're still confused about theta, think about just standard quadratic equation, minus 3x squared plus 4x plus 2. And you want to ask when this function reaches its maximum value. Why do I need and as a property that we'll use very, very heavily is that here is my function. And I ask what is its value at x0. I can ask what is f of x, but I can also ask what is f prime of x0. F prime of x0, the derivative, it gives me the slope of a line that is tangent to the function at the point P. The point P where this function is tangent to it. And what can I say about this function? If the derivative is positive, it would mean that if I'll move from x0 to x0 plus 1, say, or maybe if I'll just move a bit to the right, let's write it more, if f prime of x0 is larger than 0, playing with menu filter. If then moving to the right, by which amount I need to be careful to not overshoot it, but if I move from x0 at least a bit to the right for some small value, epsilon, move to the right, must increase f. This point x0 plus epsilon will be a better guesstimate than x0 by itself. That's if f prime of x0 is positive. Similarly, if the derivative is going down as so, then going to the left will decrease the function, for sure. And by the way, that would be exactly the idea of the steepest descent that we'll see next. How do I know that I got just to the maximum point? Because at this point, the derivative is 0. And this trick, looking for compute the derivative and ask at which x I'll make the derivative to be 0, that exactly will help me to find a closed form of that find the maximum. So I want to find the flat point of this function. Now, normally, just having f prime of x equals 0, it will find an extreme point, which might be a maximum or a minimum. For example, here I can find the derivative will be 0 over here and also over here. Both points have derivative that is 0. If the function is concave as so, then I know that I have only local extreme, and this must be the local maximum, which is also the global maximum that will be maximizing. And that would be somehow a bit, well, we'll have such luck in enough many cases. So here is a parameter. Here is my likelihood function. I just replaced x by the theta, because it's the letter that we used for the parameter. And now I am noticing that, of course, it is a quadratic function. Find the flat point. How come? What is the derivative of this function? Well, it's minus a theta square. Takes the derivative of x square. If I have x square prime equals 2x multiplied by a, that becomes minus 2a theta plus b, and that should be 0, implying that theta equals minus b over 2a. And that's called closed form. And as we said, this trick works with a gradient equal 0. Will it work for other functions? Yes, and definitely concave functions. That is, this region is convex. the region under the curve. Definitely works. And the beauty is it will work even for function of more than one parameters. Sometimes my Gaussian depends on multiple parameters, and if I want to maximize it, I'll require that in each one of the parameters the partial derivative should be 0 as well. In general, as we said, it can find extreme points, and then we need to check individually each extreme point. Hey, are you maximum or minimum? And if we have more than one maximum, it doesn't guarantee to find the global maximum. You'll have multiple points to check. Okay, let's talk about the case where we don't have such a nice and simple a closed curve, and let's instead try to talk about the steepest descent. So in general, as we said, we have the one or multiple parameters theta that we want to change, and as the case of the coin, we saw that the maximum likelihood for the data was not necessarily at 0, because 0 would mean I always get tails. It was not necessarily 1, which would mean I always get head. The maximum probability are obtained for some other theta. So what would be the steepest descent? You'll try to guesstimate a starting point and then push your theta up and up and up. And we will go kind of uphills, keep increasing theta at each step. Let's see an examples like so. More complicated functions of x, z equals function of x and y. For example, here z, which is a function of both x and y, which is minus x squared minus y squared. That's a function that you see over here. Here is some more complicated function that is a function of the probability for two parameters, theta 1 and theta 2. Back to this example. Back to this example, I want to start from some point and then do a little step in the direction of the steepest descent, that the function goes up. Another step, and until you'll get to a point where the derivative is 0 by iterative method, sequence of steps. The same, and you can start from a different point, assuming that you have more than one maximum likelihood, more than one parameter. And unfortunately, in real life, most functions that we look will have more than one maxima, but however it works. Now, what was the direction that I picked to go over here? What was a f prime tells me? Well, f prime pointed to the direction that if I'll go into, my function will increase. That is, I'm going here from some point x0, and I'll go to x0 plus eta f prime of x0, and eta will be the step size. Eta will be the step size, by how much do I want to move. Let's say 0.1. Why do I need these parameters? Because if I'll go too much, I can miss the maximum and go to the opposite side. But why do I say that? It's true because notice, if f prime is positive, derivative is positive, then this expression larger than 0, and if you'll go in the direction that is, if your next guess would be x1, which is x0 plus epsilon plus theta f prime of x0, it will take you to the positive direction. And if your f of x0 is over here, then f prime is negative, eta is still positive, so x0 will be take you to the left. Will take you from x0 to a smaller parameters. Now, in calculus 2 or 3, you are seeing that the same holds also in multi-dimensional setting, say function of 2 dimensions, but now I cannot say I need to go only to the x or only to the y. Instead, I need to look at the partial derivative. I'll take the function again, f of xy minus x squared minus y squared. The partial derivative here would be minus 2x, partial derivative by x, typo, partial derivative by y of the same function would be minus 2y. And I'll go once again from p some point I'll go from p0, which is now point in the xy plane, or p1, which is points in the xy plane in R2, then p2 would be p1 plus eta, and now I'll write a vector which is d to dx, the derivative, and d to dy, the two partial derivatives. The two partial derivatives, this vector always suggests a direction for which I'll get the maximum change. Add eta times this vector d. What is this vector d? Let's say that p1 is 1, 1. The derivatives are minus 2x, minus 2y, put 1, 1, so it's minus 2, minus 2, implying that if your second guess, p2, would be p1, which you said is 1, 1, plus eta times vector v. V is the direction of the maximum descent. So it's 1, 1 plus eta times minus 2, 2, taking me to 0.1, 0.1, which is indeed a better, will give me a better value, a higher value of f of xy in this case, and the same goes for in this case. So it's a nice property that you see in calculus. Take a vector that is a partial derivative in x, partial derivative in y. This vector suggests the direction of the maximum descent. That is, if you are insisting on moving only 1 inch, that will give you the best reward for your money. And of course, it's also the maximum descent. Go in the opposite direction, and this will be the maximum drop of the function. Okay. Now, the very same graph, except that now we are talking about the probability, our likelihood function, which is what? The probability that we see the sample giving the parameter theta. I want to maximize theta. So I'll take theta. It could be a single parameter. It could have 2 parameters. It could have multiple parameters, theta 1, theta 2, theta 3. And the jth guess is for each one of the parameters, theta here, the j here represents the, am I talking about the first, second, third parameters? My new guess is my old guess plus theta, this the side step, I don't want to overshoot, times takes the likelihood function of the and takes the derivative with respect to this dimension. This function could be, so possibly theta 1 is a mean, while theta 2 is a standard deviation. Okay, once again, the value of the new value will be the old value in each one of the separate dimension plus small step times the derivative of this function, the maximum likelihood by this function. But wait, the derivative where? The derivative in the old point. I want, this will be my new point, and I add to this the theta times the derivative of the derivative at the point, the old point. Okay, let's quick break.